grade 12 physics students, welcome to Work, Kinetic Energy, and Potential Energy in Springs. Hopefully you can hear me and follow these notes. I would request that Mrs. McDougall, the substitute, pause as the video is playing to make sure that students can get written down the notes that they need to. All right, so let's begin here. So we've already looked at kinetic energy and potential energy, and now we're going to relate all of those three things, work, kinetic energy, and potential energy in springs. Okay, so an introduction here, something called Hooke's Law, and we're going to do a lab when I return on Hooke's Law, so that's coming up. It's a relatively straightforward one. I want you to think about these three springs, and as always, folks, don't feel the need to write everything down. I'm just sort of giving you some background here. So think about the different types of springs that there are. There's the kind of springs that you stretch out, and you can see here a very skinny bald man pulling on a very large spring and a really large box. So we either stretch springs, or we can also push them and compress springs. Oh, I see I need to realign here. All right, so I just realigned. We should be good now. So strings can stretch, they can compress, or they can do both. Okay, so here the mass is bouncing up and down. The key point is that all springs follow the same law, whether they're the kind that you stretch, the kind that you compress, maybe to reduce shock or something or other, or ones that bounce back and forth. Okay, so Hooke's Law states, this is Robert Hooke over here, Hooke's Law states that it relates the amount of force F that you exert on a spring to the distance x that the spring is either stretched or compressed. So in this case here, we tend to use the letter x for distance, but you may occasionally see a d noted. X and d mean the same thing in this case. So Hooke's Law relates the amount of force that you exert on a spring to the distance that the spring is either stretched or compressed. Okay, now when you do the lab when I return, you're going to get a graph like this. I just realized that we normally do the lab ahead of time. You're going to get a nice linear relationship like this, and actually we get pretty good results. And what that means is, just get this out of the way here, from the straight line graph we get that F, the force over here, is proportional to the x. In other words, the bigger the x, the bigger the force. And this leads us to the equation F equals kx. You might remember me talking about how you turn a proportionality statement into an equation by implementing or inserting the k, which is the constant of proportionality. Now, most springs that you're familiar with, some are very strong, some are very weak. Every spring has its own constant. So in other words, it's not going to be sort of like a constant, it's going to be constant for that particular spring. And you should have found, or you will find, I guess, when you do the Hooke's Law lab, that the two different springs that I provide you with will have a different spring constant. So Hooke's Law says that the force exerted upon a spring is directly proportional to the amount that the spring is stretched or compressed. Well, of course it is. No big surprise there. The more you compress it or stretch it, the more force is required. And the constant of proportionality, the constant K, is called the spring constant. Every spring has its own constant. We think about springs like on a car that are quite strong. We think about springs like maybe in a pen that are very weak. You can almost stretch it right out and make it become a wire. Very weak spring. In this particular case, K is the slope of the line, and it happens to be 35 newtons per meter. Now I'm going to go back to this graph so I can talk about it, which is what I would normally do if I was in the class, right? So the slope of this line here is the force divided by the distance, and you'll notice that it would be measured in newtons and meters, right? So the slope here is newtons per meter. That is the spring constant, and if we were to find the slope here, it would be 35. Okay, so in this particular case, K is the slope line, and it's 35 newtons per meter. The spring constant gives the amount of force required to stretch the spring a distance of 1 meter. Now, generally nobody in their right mind will stretch a spring a meter. You would get it stretched right out where it would be unusable type of thing. But we use 1 meter as sort of the standard. So generally, spring constants are fairly large numbers, not into the hundreds or anything, but they're certainly greater than, say, like a frictional coefficient. Okay, now you should have gotten on one of the days that I was here the sample questions. These notes are a little bit different in that the sample questions are sort of embedded in the actual notes. So you should have these sample questions already. You might need to pause the video while you go and find that particular handout. All right, so hopefully you were able to find the handout, and here's the sample question. We've got a 6 kilogram mass attached to a vertical spring, and the spring stretches or compresses a distance of 40 centimeters. Find the spring constant. Hopefully your spider senses were tingling and you realize that the distance is in centimeters, so of course we're going to have to convert that to 0.4 meters. All right, so here's how you do that. We're going to write the weight force is mass times gravity. It's a vertical spring, right? We've attached it. Here's our mass, like so. We've attached it to the spring, and so it is the weight force, the force of gravity, mass times gravity, that is applying a force on the spring. So that's 6 times 9.8, or 58.8 newtons. We're solving for the spring constant. F equals kx is the formula, Hooke's law formula, F equals kx. And so 58.8 is our F, and our x is 0.4 meters. Substitute that in, and you get a K value of 147 newtons per meter. That is the spring constant for that particular spring. Again, just a reminder, every spring has its own constant. All right, so we'll move along. Maybe you needed to pause there for a moment. I hope you did. Let's talk now about work and potential energy of springs. So first of all, consider the amount of work that you do on a spring with a 200 Newton per meter constant. Work equals force times distance, and the force first exerted is found by using Hooke's law, which is, of course, F equals kx. What is the average? Oh, I guess I should show you the data here. What is this is the data here. As you stretch it more and more and more, you all know this. As you pull a spring, and just imagine a spring being stretched. As you pull them more and more and more and more, you require more and more force. And so in this particular case here, we started with 0 newtons of force. We worked our way up to 100 newtons of force. What is the average force exerted? Well, we started at 0. The initial was 0. The final was 100. Gives us an average of 50. How much work did we do on the spring? Well, we're going to take that average force, work equals F times D, average force 50 times 0.5, or 25 Newton meters of force, or sorry, of work, 25 Newton meters of work, which is equivalent to 25 joules. So is there another way to calculate this work done on the spring? And of course there is. It's under these gray boxes here. Remember that work done can be found by W equals Fd for constant force. Constant force would be a straight line graph, F times D. So in other words, if we had a constant force, it would be like this. Right? And what would F times D be? And we've seen this type of thing before. Yes, of course, you all probably yelled it out. Fd would be the area under the graph. So find the area under our spring graph. So we're going to go back to that graph and we're going to find the area, because the area is going to be the work. Work is going to be the area under the spring graph. No big surprise. There it is there. We're going to find the area of this triangle here. So the base is going to be from 0 to 0.5. The height is up to 100. It's a triangle. Divide by 2. So that's going to be 1/2 times 0.5 is the base times 100, 25 joules, which is exactly the same as what we got when we sort of looked at it from an average force type of thing. And if you stop and you think about it, the graph really, if this is, say, the initial force and this is the final force, the average is just sort of right down the middle here. Isn't it, right? So we're just kind of sort of flattening out that triangle, making it into a rectangle, finding the average. Okay, now let's talk about this algebraically. if the area of a triangle is 1/2 the base times the height. And the base of that triangle, remember this is force multiplied by distance, and again, pause as you need to make sure you get this stuff down. The base is the distance, and the height is the force. So the distance, we're going to represent that by the letter x. The force is from Hooke's law, kx, and now I've got 1/2 times x times k times x, or the area is 1/2 kx squared. I'm trying to remember to go slow here because I don't have anyone in front of me while I'm teaching this. And yes, it's kind of weird being in here on a Monday teaching to nobody, but hopefully you're listening to this on Thursday or Friday or one of these days coming up. So the spring energy is 1/2 kx squared. Now you might wonder what this US is. I'm hoping that you just heard me a day or so ago, which is in my future, kind of some time traveling going on here. U stands for potential energy. Sometimes we use PE for potential energy, but U is often used for potential energy, and the S simply represents that it's a spring potential energy. So spring energy is 1/2 kx squared. US is the amount of potential energy stored in the spring, and you know that when you stretch a spring, there's energy stored in there. When you compress a spring, there's energy stored in there, depending on what the sort of the base setup is of the spring, and that energy is known as potential energy, or US. Okay, so go ahead and find sample number 2. Should be right after sample number 1, so that shouldn't be that hard to find. And the question is, if you do 24 joules of work in compressing a spring whose constant is 80 newtons per meter, how far is the spring compressed? We are solving for the x, the distance. Right? So our potential spring energy formula is US equals 1/2 kx squared. 24 joules of work is done, so we're going to substitute 24 in for the US. 1/2, the spring constant is 80. We're going to solve for x. So 1/2 of 80x squared, I guess that would be 40x squared. We're going to divide by 40, take the square root, and you should get 0.77 meters. And I would recommend pausing here, making sure that you got the math done correctly on that. All right, let's move on. So sample number 3 should be right on the sheet there. Similar kind of question. I've got one in front of me here. A spring with a spring constant of 200 newtons per meter has been compressed 0.1 meters. How much work must you do from this point to compress it to the 0.4 meter mark? How much work must you do? And the key words here are from this point to compress it to the 0.4. So it's going from 0.1 to 0.4. Now you might think your first instinct might be to subtract and get that 0.3 and then go with that. Let's just see what happens here. Okay. Now, this is a key idea right from the day one, that work is done when energy is transferred, and so in this case here, the amount of work done is the potential spring energy gain, actually gain. So what you have to do is find out how much work, how much potential energy it has before. That's USI, initial spring energy, 1/2 kx squared. This is 1/2 times 200, and the distance is 0.1. That's the initial distance that was compressed. And if you work that math out there, you get 1 joule. So that's how much energy was in the spring to begin with. And then the final spring energy is at 0.4, so that's USF, final spring energy, 1/2 kx squared, 1/2 200 times 0.4, and you get 16 joules. So it started with 1 joule of energy stored in the spring, and it ended up with 16 joules of energy at the end, which means how much work did you do? You did 15 joules. Okay, so that's how you do something like that. Now, you should note you can't just substitute 0.3 into the formula, since this represents the delta x, not the total compression. So if you were to do 0.3 in there, that would be how much work would be done to compress it from 0 to 0.3. So you can't actually do that this time. You have to actually find the initial and the final and then subtract. Okay, so now let's look one more thing here. Work, potential energy, and kinetic energy in mass spring interaction. So now we're going to throw it all together in one sort of big pot. Think about a mass colliding with a spring as shown. I'm going to show you the picture right here, okay? So this is my very weak attempt at drawing a spring right here. And the little square has just reached the spring. The spring has not had any compression happen yet. So before the collision, all of the energy is kinetic. It's just touching the spring. The spring has done no compression just yet. During the collision, the kinetic energy of the mass decreases as it sort of runs into the spring. It slows down. The kinetic energy of the spring of the mass decreases as it does work to compress the spring. So you can see here that the spring is slightly compressed, right? And there's the block that's moved a little bit to the right, and it's actually slowed down. Now note that energy must be conserved, conservation of energy. So ET, total energy, is equal to EK, kinetic energy, plus potential energy. I guess that should technically be a US. And recall from before that kinetic energy is mv squared over 2, and spring energy is 1/2 kx squared. Now, these are both written the same. I'm not sure why. They're written differently. You could write this as 1/2 mv squared, and that could be 1/2 kx squared, or this could be kx squared over 2. They both mean the same thing, right? Times by 1/2, divide by 2. Same thing. Okay, this is just a review, a replay here of what I had in the previous screen, just so we can compare it all together. What happens at the end? So at the end of the collision, all of the energy is transferred to potential energy. This is now the end. You can see that the box is no longer moving. There's no arrow. The spring is even more compressed. At the end of the collision, all of the energy is transferred to the potential, to the spring, and the kinetic energy is 0. And that happens when, or in other words, the initial kinetic energy, EKI, initial kinetic energy, is equal to the final spring energy. Or in other words, 1/2 mv squared is equal to 1/2 kx squared. I'd suggest you pause there for a moment and just sort of think about that for a second. Okay, so here is sample number 4, the last one. Here we have a 5 kilogram mass that's moving at 5 meters per second. It strikes a spring bumper, having a spring constant of 50 newtons per meter. So it's running into something and to bounce off of. Find the kinetic energy of the mass before collision. Find out how far the spring will compress, and find the kinetic energy of the mass after compressing 0.8 meters, sort of in a part-way situation. So part A, kinetic energy of the mass before collision. Kinetic energy is 1/2 mv squared, or mv squared over 2. That's pretty easy. 5 times 5 squared all over 2. Should get 62.5 joules, is how much kinetic energy there is before. And so the question, how far will the spring compress? All of that kinetic energy has to turn into potential. Note that this is a horizontal type thing. If it was vertical, you'd have to be worried about potential energy and gravitational height. And I know there's a question in your future about that. But for this case here, it's horizontal. So let's just see what's underneath the box here. The initial kinetic energy, this should probably have one more line above it here. This would be EKI, the initial kinetic energy, is all transferred to final spring energy, USF. So the 62.5 kinetic energy, 62.5 joules of kinetic energy is transferred to spring energy. We're going to solve for x, which is the distance, and you get 1.58 meters. That's a lot of compression. This spring would be relatively weak, which is why it takes so far for it to stop. Okay, so now the kinetic energy of the mass after compressing the spring only 0.8 meters. So if it were to stop, it would have to go to 1.58. It's not stopping, it's only going to 0.8. How much kinetic energy, or in other words, how fast is it moving when it's still only compressed at 0.8 meters? Okay, so I'm going to write E, or ET might be a better way to say. Total energy is the kinetic energy plus the spring energy, US. What is the total energy? 62.5. That's how much kinetic energy there's at the start. That's how much spring energy there is at the end. So that's going to be 62.5. We're going to solve for EK. The spring energy formula is 1/2 kx squared. We know the distance is 0.8. So I'm going to plug in my 0.8 and my 50 in my K value. I'm going to find out what that number is over on the right there. It's 16. And then take it to the side and subtract, and you get a kinetic energy of 46.5 joules. Now, if the question asked you how fast it was going, you would use mv squared over 2, put that 46.5 in for the EK, and you would solve for V. Relatively straightforward. You should be able to do that. All right, so that is the end of the spring energy notes. Hopefully you were able to follow that along and get a reasonable amount of knowledge out of that. Take some time to do the spring questions that are there on that same attachment. Robert Hooke is in the corner to help you. As always, there are answers on the back as well as a link and a scan code to get to solutions. I encourage you to use those. Good luck with all that, and I will see you when I return. Oh, I should probably throw in a bad joke just for Connor here, so how about I say something like, Connor, get to work.